Okay, so here we have a problem. It's another momentum problem where we have two cars. We have this car that's going down. So there's a road and there's an intersection, and then the cars are going to collide in the intersection. So what we have here is this car here that's 1,500 kilograms, and its speed is, or its velocity is v1. As you can see, it's going south. And then there's another car, 2,200 kilograms. That's its mass, and it's moving to the west, and it has a velocity of v2. Now, once these cars collide, they're going to go in this direction, southwest. And they're going to slide. So they're going to lock up, and then they're going to slide. And they're going to slide 5.39 meters to the west and 6.43 meters to the south. Basically, what we need to do is we need to figure out what V1 is, the velocity of the blue car, and V2, the velocity of the green car. The other thing that's given is that the coefficient of kinetic friction is 0.75. So that's the friction between the tires and the ground. Okay, so let's go on this. So first of all, what I probably want to do is find out. Actually, this is not V3, but this is like I want to find out. I want to find out the length of this arrow. So how far did what was the actual displacement of the car? I mean, we know it went 5.39 meters west and 6.43 meters south, but what was the actual displacement that the car went? Okay, so how do you do that? Well, this is just Pythagorean theorem, right? It's a triangle, so you just do a squared plus b squared equals c squared, right? And so you just do 5.39 squared plus 6.43 squared, and then you take the square root of that, and you should get 8.39 meters. And that's the total displacement. That's how far the car actually traveled. Well, the two cars, this is how far they actually traveled together. They actually moved 8.39 meters. Okay, so this is a momentum problem. So remember, in momentum, you want to look at the momentum of the system before the collision and then the momentum of the system after the collision. So what's the system? Well, the system is the two cars. So car 1, which we'll call V1, or that's the velocity of that car, and then V2. So, but another problem here is that we're actually dealing in multiple directions, right? We have an up and down, a left and right, or an X and a Y axis. So how this works is because velocity is a vector, right? So remember momentum, P, is equal to mass times velocity. But, well, mass is a scalar. It doesn't have a direction, but the velocity is a vector, so it does have a direction. So therefore, because velocity is a vector, momentum is a vector as well too. So what we have to do is we have to actually analyze this problem in the x direction and in the y direction. And what happens is that momentum is actually conserved in both locations. So momentum is conserved in the x, and it's also conserved in y, and also it's conserved in total in when you combine the x's and the y's. Okay, so remember, momentum is conserved in the x. It's conserved in all directions. Okay, so what we want to do is we want to look at it from the x point of view and in the y point of view. So I have the mass times v1, the velocity of that car that's attached to that mass, plus m, the other mass, times v2 times the car that has the v2 velocity, which is the green car, equals. Now the two cars are basically going. So this right here is before the collision in x. And this over here is after the collision in x. So after the collision, they're going to link up. So basically, you have the two masses are going to link up. right? So you're gonna have m plus m. They're not. It's not m plus m, but it's both the cars. And then those cars are gonna be going some velocity. I'm gonna call that v3. Okay, and then the same thing is over here in the y2. So we can say mass. Well, there's a before collision, and then there's a after collision. Okay, so I'll say mv1 plus mv2 is equal to m plus m v3. Now you might be thinking to yourself, well, yeah, but the blue car is going down, so isn't his velocity negative? And let's do a minus sign there. And isn't the green car going to the left? And isn't that negative as well too? Well, if these things are negative, then they'll actually show up in the velocity itself. So v1, if v1 is negative, then it will make the whole thing negative. So don't actually write negative here, because if v1 is negative, then it'll say negative, and then that's a negative, and I'll make it positive, which isn't correct. So if v1 is negative, then it itself will be negative. Okay, you don't have to say negative. So it will actually by itself just be negative. So don't actually put that in. Okay, because momentum is the total momentum of the system is the momentum of all the different objects. Okay, so let's look at the X one first. So this blue guy that's going up and down before, is he moving in X? No, he's just moving up and down. He's just moving in Y. So there is no X. So this guy is actually 0. Plus, now, the guy in green, is he moving in X? Yes, he's moving in X. Now, you might be thinking, I'll do negative. No, don't do negative, because the negative will be a part of the V2. So I'm going to do its mass. So its mass happens to be 2,200 kilograms, and his speed is V2. And then you're going to add 15. So after, they're going to come together. So 1,500 plus 2,200 is 3,700. And that's V3. Okay. And then over here, I can do the same thing. In Y, we have 1,500 V1 plus, and then the green car is not moving in Y at all, so that's 0. And then once again, this is 3,700 V3. Now, V3, this velocity 3, it's not actually, well, what you want to do is V3, this thing here, is actually, we want to look at it from the X perspective. And in this case right here, we want to look at it from the Y perspective. So how can I say V3, but I don't want V3. I want V3 kind of, I want just the X part of V3. Okay, so I'm just going to undo this so it's not super messy. So how can I do that? Well, because the displacement over here, if we're looking at where this red thing is, right here. If you're looking at this thing right here, if you're looking at this red thing, if that's the displacement, right? If the car is being displaced from here to here, then obviously the velocity is also pointing in this direction as well too, right? And so how could I get just the X component of V3? Well, you could just do, you could pretend that there is some alpha here, there's some angle, and I just want the X component of it. Okay, so what I'd like to do is I'd like to find out alpha, like what is this angle for my V3. And so what I can do is now I don't know the length of V3, its actual length, because I don't know what it is. I don't know what V3 is. But I do know that it's 5.39, whatever it is, it's 5.39 in the X and 6.43 down in the Y. So what I could do is I could just say, well, the tangent of alpha is equal to, of course, opposite over adjacent. And opposite is of alpha is 6.43. And adjacent is 5.39. Okay. And then if I want to get alpha by itself, of course, I'll do the inverse tangent. And so then that means that alpha is equal to the tangent inverse of 6.43 divided by 5.39. Okay, and so that's alpha. And then if you do that, it actually turns out to be alpha actually ends up being 50.02 degrees. Okay, so now I know what alpha is, right? So I just figured that out. And so now that I know that, then I can come back down here and say, well, if I want to know what V3 is, just the x part, I would say V3 times the cosine of alpha, which is 50 degrees, 50.02. And then conversely, over here in the y, I would say 3,700 pounds times V3 times the sine of 50.02 degrees, okay? And so now that's correct, right? So now I have this formula over here, 2,200 V2 equals 3,700 times V3. And it's not V3, but I want just the x component of V3. So it's V3 cosine 50.2 degrees. And then over here, I have 1,500 V1 equals 3,700 V3 plus, 3,700 V3 times sine of 50.02. Great. The problem with this now is that I have one V2 and I have V3, two unknowns, and I have V1 and V3, two unknowns. So basically I have V1, V2, and V3 are unknown. But I have two equations, so I can't solve it because three unknowns, two equations. I need three equations, okay? So maybe someone can help me out with another equation. So what we're going to do here is we're going to say, okay, so I mean this is good, but now we need to do something else to help us get us over the hump. Now, what's going to happen is these guys are going to have some kinetic energy, right? So you could say that, you could say oh, this is the kinetic energy of car 1, and then you could add in the kinetic energy. This is like a bar graph. The kinetic energy of car 2, and maybe that's like a, obviously a larger amount of kinetic energy. Kinetic energy 3, okay. So these two come together and they hit. The problem is that there's a loss, right? Is when these guys collide, you're gonna lose energy, right? So maybe there's this much energy you're gonna lose. How much are you gonna lose? I don't know. I don't know what it is. So you can't use the law of conservation of energy in this problem because you're gonna lose something, and so because you're losing it, you don't know how much. You can't solve it using this. But what you do know is after the collision, yes, some amount of energy has been lost, but whatever is left over, okay, let's say this is the leftover energy after the collision. Okay, so let's write that down. This is the leftover energy after the collision. Okay. And it's going to be some form of kinetic energy, obviously, because it's moving, right? Because these cars are moving, they're going to link up, and they're going to continue to move. So they have kinetic energy, right? So yes, it did lose some energy. How much it lose, we don't know, but it still has some amount of kinetic energy left because it's gonna move, and it doesn't have potential energy, right? There's no potential energy. All it has is just kinetic. Okay, so it has this well of kinetic energy, and what's going to happen to it? Well, it's going to bleed off due to friction, right? So the force of friction is going to cause that kinetic energy to go away, right? So there's, if I were to do some sort of graph here, where this is the energy level here, and then this is the distance. X is the distance. As the distance increases, my kinetic energy goes lower, lower, lower. I don't know what the graph looks like, but it's eventually going to go to zero, right? I have some amount of kinetic energy, and then as we keep moving in X, or as we just keep moving on the ground, right, our kinetic energy is going to bleed off until we have no kinetic energy, right? And then we've stopped, right? Now we have no more energy left. It's all been dissipated into heat. Okay, so what we can do is we can say, what force is causing this kinetic energy to go away? Well, that force is friction. So friction is going to do work on the kinetic energy. And so what does that friction look like? So what we can do is we can do a free body diagram, right? So this represents the two cars together. Obviously the cars have some weight, which is mg, which is their total mass, which is 3,700 kilograms times gravity 9.8. And this is basically 260 newtons. And then up here on the top, because the car is not accelerating up or down, that means these forces, due to Newton's first law, they have to be equal. So the normal force has to be the same, in this case here, has to be the same as the weight, which is 36 to 60 newtons. Okay, got that. Now, and because we know the normal force, we can figure out the force due to friction, Fk. This is the friction due to, this is the force due to kinetic friction. Okay, and that's mu sub k, which we already have, which is, it's up here at 0.75. Yep, they gave that to us. Times the normal force, okay? And if you do 0.75 times 36,260, you end up with 27,195 newtons. Okay, and so this frictional force is going to completely drain the kinetic energy until it's gone, right? So as the car is moving, let's imagine the car is here and the car is moving in whatever, it doesn't matter what direction it is. I mean, we do know it's going southwest, but it doesn't matter. We do know that the car is moving in it's making some displacement, right? And then what displacement is it? Well, we saw it up here. It's 8.39 meters. So it's 8.39 meters. The car actually moves on. And as it's moving, it's going to drain the kinetic energy, right? It's going to do work on it. Okay, it's going to do work on the car and cause that kinetic energy to be dissipated. Okay, so and it's moving parallel. So while the car is being displaced in this direction, the force of friction is actually going in this direction, right? So it's not helping it. It's impeding it. It's making it go slower and slower and slower. Where if the force were going in this direction, obviously it would make the cars accelerate. But because it's going in this direction, it's making the cars deaccelerate because they're getting slower and slower and slower. So if you were to look at this from a graph perspective, this is the force, and then this over here, x, this is or distance, yeah, x in meters, of course. And the force, of course, is 195 newtons. And it's the same, right? It's the same force. So that force doesn't go up or down. It's the same frictional force because the cars weigh the same no matter where they are. Here, the cars weigh the same. So the normal force is the same. And if the normal force is the same, that means the frictional force is the same. So it doesn't matter where the car is. It's still going to be the same force. So the force is constant. And how far is the force going to be acting on this car? Well, 8.39 meters, which is right here. We'll call that 8.39 meters. So this is a rectangle, right? We can say 27,195 times 8.39, and that gives you 166 joules. So that's how much work friction did. So if friction did that much work, it had to get it from somewhere. It's like it's spending money. So it's like friction spent $228,000. Where did it get the money from? This is just an analogy. Well, it got the money from kinetic energy. Kinetic energy gave it to it. It says, "Oh, I have $228,000," and then the friction said, "Great, I'm going to spend it all." And then once it spent it all, so to speak, now it's all gone. Now the money, quote unquote, the energy is now gone. So this that friction did use, it used to be kinetic energy. So I could say 228 166 used to be kinetic energy, which is 1/2 mv squared, right? And so in order to find that v, you would just multiply times 2. That's parentheses. Get rid of that. Divide by the mass, which is 3,700 kilograms. Get rid of that. The square root it, and now you end up with v. Now remember, this is the velocity after the collision. And if you do that, you'll get 11.10. 11.10 meters per second. 10 meters per second. Okay, so that's the velocity. Now, you might be thinking, well, this is actually v3. This is actually v3. And so remember that this is the velocity of the combined cars after the collision. So this v3 is actually this vector here. So it's like, so if this is my coordinate system, this here is v3, which is 11.10, which is 11.10 meters per second, right? But what we're going to do here is we're going to do 11.10 right here. V3, it's 11.10, but we're going to get just its x component. We're going to do cosine 50.02 and get just its x velocity. And then over here, we're going to do 11.10 times the sine of 50.02. We're going to get just its y component. So remember, 11.10 is actually the length of the vector, but we need its actual components because we need to figure out what it is in x and y. Okay. And so once you know v3, okay, v3 is now given. And so once v3 is given, then all we need is v1 and v2, two unknowns, but we have two equations, right? So now we don't know v1 and v2, but we have two equations. And what happens is you pop those in, and you'll get v2 over here. You'll get a v2. You'll solve it, and you get v2 of essentially 12 meters per second, and over here you'll get a v1 of about 21 meters per second. Okay, and that's basically it. So to recap, this problem involves a conservation of momentum, but we're actually pulling it out and doing momentum in the x direction, in the x component, and in the y component. Okay, so we're separating them out. So conservation of momentum is conserved in x, and it's conserved in y. Okay, so we did that, and then we figured out, oh, we have this much money, not this much money, but we have this much energy after the crash, this much kinetic energy. We don't know how much was lost. That's fine, but we do say, okay, I had this much kinetic energy, and then friction used it all. And we figure it out because the way the car, we knew the normal force, and therefore we automatically calculated the force of friction, which is 27,195. But then we took that 27,195 and it was applied over some distance, 8.39 meters. So it had to have used 228,000 joules of energy. It had to have used it. But where did it get it from? Well, it got it from kinetic energy. And so that kinetic energy was the energy right after the collision. And then once I did that, I figured out V3. And then once I figured out V3, then we could figure out V1 and V2. So this is basically how you use momentum and energy to solve a problem involving multiple dimensions.